Welcome back. This is the Tutor Wizard. I'm Adrian. This is Alice. Please subscribe right here. We're doing Math 102, which is mathematical motive. Right now we're going to do early numeration systems. In particular, this lecture, what we're going to do is numeration systems, conversions between bases, and arithmetic and other bases. Let's get to it. All right, for numeration or positional systems base B, what we're essentially doing is we're picking a positive integer larger than or equal to 2. So you can pick 2, 3, 5, 7, it doesn't matter. We're going to stick to, usually in these videos and in my classes, base 7 and base 11, because they're both prime numbers and one is less than 10 and one is larger than 10. Once I pick a base B, we have to pick base B digits, and we're going to pick the 0 as a placeholder, which is the epiphany, and then we're going to do the digits from 0 and then 1 to b minus 1. So if you pick 7, it'll be 0, 1, 2, 3, 4, 5, 6, because 6 is 7 minus 1. Then what we're going to do is we're going to use the powers base b, which are going to be b to the 0 is 1, b to the 1 is b, b squared is b times b, b cubed is b times b times b. In decimal, we call this the 1 spot, the 10 spot, the 100 spot, the 1000th spot. Once we have that, we can write any positive integer as follows. N is equal to this positional system, that's what we're going to call it, positional or numeration system, a string of digits essentially. Then we write the brackets to indicate base B. Once we've done that, what that really means is we're multiplying by increasing powers of B, is essentially what we're doing. B to the 0, B to the 1, dot, 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 B to the K is secretly what's happening. Then once we multiply all those digits, which are in the set 0 to b minus 1, we might multiply those digits by the powers of b, then we add that up to get essentially what I'm going to keep referring to, how many apples are in the basket. This notation is horrible, I understand, so let's do an example of this right away. Alright, example 1 is positional systems base B. They have a fancy name for everyone, but I'm not going to give them unless there's specific ones that we talk about regularly. Base 7 is heptary, I believe, and base 11 is onary, but you don't have to call them yet. You can just call it base 7 and base 11. So binary just has 2 digits, 0s and 1s. Binary digit becomes bits, is the terminology. In ternary, we're base 3. We're going to use the digits 0, 1, 2. 2 is, remember, 3 minus 1. So we always go from 0 to b minus 1. In base 7, we're going to still be, 7 is still less than 10, so we're going to use the digits 0 to 6. In classical base 10, if we squeeze that in there, base 10 is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The Hindu Arabic symbols, they're actually also right here, and one that's larger, or here. But notice now when I use base 11, I have to use the symbols 0 to 9, but 10 can no longer be 1, 0, because that means one group of 10 and no 1s in base 10. Now we have to write it as a single symbol, in which we're going to call alpha. It's going to be 10 now. And then, of course, another example is hexadecimal, which is used in computers for computing. And we're going to use the symbols A, B, capital letters A, B, C, D, E, F for the numbers 10, 11, 12, 13, 14, 15. Again, why? Because base B in base 10 representation, which you're used to, is always 1, 0 base B. Because this is why. And of course, the classic joke is there are 1, 0 kinds of people in the world, those who know binary and those who don't. So this is examples of positional systems. Computers like to use base 2 and base 16. Our species, for the most part, like to use base 10. And in this class, we're going to use base 7 and base 11 to do arithmetic and see how these things work. Let's get to, first of all, how do we convert back and forth between the bases? All right, example 2 is going to be conversion from, we'll do the easy one first, from base B to decimal representation. The only tricky part is when you have this alpha in there, or when you have symbols in a larger base, you have to turn them back into their base 10 representation. So how do we do this? Solution for 1, what we're going to do is we have 2, 3, 4, base 7. What that's actually equal to is, or how you can remember, is I'm always going to use, this is going to be 7 to the 0, 7 to the 1, 7 squared. Then what I'm going to get is, therefore, this string of symbols, by definition, base 7 is equal to a base 7 digit times 7 squared, plus 3 times 7 to the 1, plus 4 times 7 to the power 0, 7 to the power 1. So this is going to be 2 times 49 plus 3 times 7 plus 4, which is going to be equal to 98 plus 21 plus 4. And if you can't see, if you're going to do this, do a side calculation, we're going to have to do this in a different base right away anyways, but base 10, this is going to be 98 plus 25, so I'm going to get 13. I carry a 1, a group of 10 over, and then I'm going to get 9, 10, 11, 12. So I get 1, 2, 3. Where's this guy? So I could have left it, but this equals 123. For the other one, what we're going to do is 2. I get 1 alpha 2 base 11. What that tells me again is I have 11 to the 0, 11 to the 1, 11 squared, which is 121. So I'm going to get, this is equal to 1 times 11 squared by definition, plus alpha times 11 to the 1 plus 2 times 11 to the 0, which is now equal to 11 squared is 11 times 11, which is 121, plus 10. This is now a 10, remember, in base 10. And then finally, so that's going to be 110, 10 times 11, and then plus 2. Again, if I can't see, 121 plus 112 is going to be equal to 33. So we're going to get equals 233 base 10. I don't usually write in the base 10 because the decimal form is the familiar one. So if I leave it off, I mean base 10. So 1 alpha 2 is 233 apples are in the basket, and 234 base 7 is actually 123 apples in the basket. This is how I convert from a strange base to familiar land base 10 representation, or decimal. Example 3 is going to be convert from the decimal representation now to base B representation. So how do we do this method? We're going to use iterations of the division algorithm, finding quotient remainders when we divide a number B into a number A. Solution 1. So I want 23 into base 2, so I'm going to divide 2 into 23 to get a quotient and a remainder. 2 goes into 23 11 times 2 is 22 plus a remainder of 1. Then I use the next quotient is what I divide 2 into. 2 goes into 11. So 11 is 5 groups of 2 plus 1. And then I use the 5. 5 is 2 groups of 2 plus 1. And then finally, 2 is 1 group of 2 plus 0. And then this guy is finally where I can stop because it's less. So 1 is no groups of 2 plus 1. Once I get a 0 quotient, I know I can stop, and this tells me that the number in reverse up this way is going to be 23. Let me put it here. This says that 23 base 10 is equal to 1, 0, 1, 1, 1 base 2. Alright, for the next one I can squeeze it, and I was going to try and do them underneath. So, for 109, 109 is, if I actually can't see this now, what I have to do is side calculations. So, I'll do it here and erase it. I have 7, and I have 109. It's also good to list the multiples of 7 first. 7, 14, 21, 28, 35, 49, 56, 63. So now what I'm saying is, how many times does 7 go into 10 without going over 1? I get 7, I subtract, I'm going to get 39. I'm going to bring this down, it should be a 5. I'm going to get 35. I subtract, I get a 4. So what this says is the quotient or remainder when I use the long division every time is going to be 109 is 15 groups of 7 plus 4. And then once I've done that, I can, once the numbers are reasonably small, I can probably get that in there. So this says 15 now is going to be equal to 2 times 7 plus 1. And 2 is equal to no groups of 7 plus 2. So what that says is 109 base 10 is equal to 214 base 7. For the last one, 142 is going to be 12 times 11 plus 10, which has to be written as an alpha now, not 1, 0. Then I look at this. and I say, you can leave it like that, but you have to convert it at the end. Remember that it has to be a 10, or 10 is an alpha, sorry. And we have 12 is equal to one group of 11 plus 1, and 1 is equal to 0 groups of 11 plus 1. What that tells us is 142 base 10 is equal to 1 alpha base 11. And this is how we convert from decimal to the other base. In each one, we use iterations of the division algorithm, finding quotient remainders when I divide one number into another. Who's dividing who? Every time we do it, the base B is who we're dividing into everyone, and we use the original number, then we use the quotients in every step to get this till we get 0. This is how I convert from decimal to base B. Alright, to finish off, what we're going to do is adding and multiplying base 7. It's the same for base 11. We'll do this eventually or in another video, but for now, to finish off, we'll show you how to do the arithmetic and other bases. What the key is if once we pick a base, b equals 7, we have to relearn or memorize or write for ourselves the addition and multiplication tables base 7. So when I add, remember 1 plus 6 is 7, but that's one group of 7 plus 0, so that's 1, 0. Over here, same thing, I'm multiplying. 4 times 4 is 16 in base 10, which you're used to. But when I look, it's why is it 22? Because that's 2 times 7, which is 14, plus 2, which is 16. So 4 times 4 is still 16 in base 10 representation decimal. But in now our magic table, 4 times 4 base 7 is going to be 22. Remember the 2 represents base 7 is 2 times 7 to the 1 plus 2, which is 14 plus 2, which is 16 base 10 is what I'm saying. So this table hasn't changed. Worlds are not colliding. It's the same numbers, but you have to learn to think in base 7, not base 10. Now, when I'm adding, I immediately rely on these tables. So when I add, I look 4 plus 6. 4 plus 6 is 13, which means one group of 7 plus 3, which is 10, but I get 13. I carry the 1. I'm carrying the group of 1 because these two one-digit numbers, their outcome ended up being a 2-digit number, which I can't write in the one spot. So I write that guy, and then I carry the one group of 7 over, and then I get 1 plus 1 plus 1 is a 3 again. And then I get 5 plus 2 is 7, but that's 1, 0. Again, 2 plus 5 is 1, 0. So 1033 is the answer to 214 plus 5, 16 in base 7. Now when I multiply, this gets even worse. So I want to do 6 times 2. 6 times 2 is 15. I carry the 1. 6 times 3 is 24. And then I've got plus 1, so that's going to be 25. And really what that means is 14, so 19 is what it actually means in decimal. You have to remind yourself. Now in multiplication, remember, the 1 is now in the power 1 of the 7s, not in the power 0 7s. I want to say the 1's in the 10 spot, but I mean the 1's in the 7 spots, I guess. So we have to write a 0 down there because it's not going to contribute to the 1's anymore. It's going to contribute only to the power 7's. Luckily now I get 1 times 2 is 2, and 1 times 3 is 3. And then now in multiplication, it's actually addition, so now we have to add. If it spills over, still now we're adding in base 7 still. So 5 plus 0 is 5. 5 plus 2 is 1, 0. So I carry, and then I get 6. So 32 times 16 in base 7 is 605. Please subscribe right here. I'll see you next time.